I could walk another month or two.
It's not fair.
It really works better if we skew it to the stage left.
Terrible lighting for video.
What's that?
I say it's terrible lighting.
Yeah, the rooms are a challenge, but those is good this way. There's no problem. Doing stereoscopic, I couldn't
Oh,
hold it.
no.
Okay, the next presentation is a contribution from University of Virginia, back Neurock, continuing on the theme of sintering. The title of this talk will be Elucidating Mechanisms that Control Metal Sintering.
Thank you. It's wonderful to come after Stu. He did a fantastic job of outlining a lot of the complexity that exists in these systems. I won't come close to any of that, but I'll talk about very fundamental studies whereby what we're trying to do is to use theory, simulation, coupled with experiments to try to elucidate ideas on mechanisms that may control metal sintering on oxide surfaces. And in particular, we're going to focus on ethylene epoxidation, looking at silver particles on an alpha aluminum oxide support. The work is a collaborative effort between people in my group, UKAI and Randall Meyer, as well as CRI International, which is an affiliate of Shell Global Solutions. And that's John Lockmeyer, Donald Rinalda, Randy Yates, and Mike Lemansky, who's here, I believe, in the audience. And so what I want to do is present sort of the combined effort that we've been looking at in terms of some of these processes. This is some beautiful work that was done by Donald Rinalda on well-defined surfaces whereby he's deposited silver particles, and as you saw from Stu's talk, you get coalescence, or you can get these particles growing. And how they grow is one of the interests of concern for us. So this is done, these are silver particles on an alpha aluminum oxide support, and that's going to be our focus. And this is looking at conditions that are relevant for ethylene epoxidation. Stu pointed out the two predominant mechanisms that are described. There's coalescence, which he very nicely showed how this can lead to larger particles. And then there's Oswald ripening, whereby you get smaller particles that find their way off of the small fragments that find their way off of the small particles and migrate to the larger particles, or they can go through the vapor phase and ultimately give you growth of the larger particles. Now, so this is a nice match of what Stu showed. Everything else I'm going to show perhaps is going to be a different solution. So these are some of the results from the experimental studies. Some of the characteristics of Oswald ripening are that when you look at a particle size, the ones that are larger than some critical radius, if they're growing, they grow as a function of time, and the particles smaller than that critical radius shrink as a function of time. And that's why you want to look for those smaller particles. If you look at the ratio of the radius to some R0 radius, this should change in terms of Oswald ripening as a factor of t to the 1/3 power. In terms of coalescence, it's t to the 1/7 power. Here's a plot of that data, and you see that it's much closer to essentially characteristics of Oswald ripening. In addition, if you look at the particle size distribution, in terms of Oswald ripening, what you would find is a tail towards the smaller particles, and that's what we see here. For coalescence, what you would find is a tail towards the larger particles. So at least for this system here, the model experiments that were done here, it looks closer to being Oswald ripening than coalescence. So we want to use theory to try to understand some of these factors that control the kinetics of these processes. And so some of the things that we have to concern ourselves with are diffusion of metal species, mobile species, from a larger or small particle down along the particle to the base of the interface of the metal-metal oxide, the detachment of some mobile species from the small particle onto the support, and then the diffusion along the support, and then ultimately the reattachment of that ion. So that's essentially the mechanisms for Oswald ripening. We also have coalescence, or the spreading and the touching of these particles that can lead to particle growth. So our approach is to use theory, periodic density functional calculations. I won't go into the details there, and ultimately what we're doing is combining that with kinetic Monte Carlo simulations to track the dynamics or kinetics in these systems. Going the wrong way. So the first part I'm going to look at is really the diffusion of mobile intermediates across the surface. We look at various different terminations because we don't know what's on the surface as a function of time, and as Stu pointed out, the more oxidizing conditions may lead to sort of wetting of the surface. So under vacuum conditions, you get an aluminum terminated surface for alpha aluminum oxide. Under higher oxidizing conditions, you might form an oxygen terminated surface, and under a number of conditions, what we see are hydroxyl groups of various given degrees, and that can all of these can ultimately play a role in terms of diffusion of mobile intermediates on the surface. So this is just the one step of mobile intermediates. We start with a single atom, and this atom can diffuse across this oxide surface, and that's what I've shown you here in this diagram, 1 to 2 to 5 to 4, and we can calculate what the overall energy barriers are for each of these jumps. And overall, we get something on the order of about 0.3 eV, which is a very easy barrier to overcome. Any one of these energies are very weak, so this is not very tightly held to the surface. So under UHV-like conditions, if you've got exposed aluminum, these things move quite readily if they ultimately find the support in this way. We get diffusivities that are on the order of 3 times 10 to the minus 8, and this matches some nice work that was done in the literature looking at platinum diffusion and the diffusion coefficients that they measured there for exposed aluminum surfaces. If you have an oxygen-terminated surface, you find some significant changes and differences. The binding energy here of the metal to the surface is about an order of magnitude larger. It's almost 5 eV. And if you look at its diffusivity from site to site to site, the biggest gap here is on the order of about 2 eV. So there's a significant barrier that's going to prevent it from ultimately migrating, but that strong interaction would ultimately facilitate, as Stu pointed out, sort of the wetting of the surface. So we need to concern ourselves with what is the surface under working conditions. And so we carry out ab initio thermodynamic calculations whereby we can dictate what the partial pressure is in the system and the temperature, and you can examine the phase space in the system. Here we're varying the partial pressure of oxygen. You find that you get aluminum termination when you get very low partial pressures of oxygen, and as you might expect, when you go up in terms of the partial pressure of oxygen in these systems, you start to terminate with OH groups. And you see the same thing if you were to vary the partial pressure of water in the system. The surface that ultimately dominates at some point is, you see 1, 2, and 3 hydroxyl groups terminating the surface. So we ultimately one might expect that you've got hydroxyls that are interacting with the surface. So we look at diffusion along a hydroxylated surface and within a hydroxylated surface and calculate some of those barriers. Here we see that the barrier to escape from a hydroxylated region is on the order of about 0.4 eV. So I don't have time to go through all of the details, but we've got essentially diffusion of the single silver atom along different sites. So what is their binding? And here are their diffusivities on the aluminum terminated surface, the oxygen terminated surface, as well as various different hydroxylated surfaces. And we can estimate diffusivities from this that we would like to use later in terms of simulating what is the mobility of these species. So that's a single atom. We've done this now for 2 metal atoms. These 2 metal atoms can ultimately migrate on the surface in a couple of given ways. They can translate, which means they just simply push their way across the surface. This costs us an energy barrier of almost 1 eV on this surface. There's an easier way for them to move, and that is to rotate. So this atom here is rotating downwards as we continue along the slide, and they ultimately end up in the same spot, and they're moving, as Stu pointed out, biology, as an amoeba. And so we see the same movement. The barrier here is significantly lower than the case where they ultimately translate as one fixed unit. So we've done this now. This is a small movie of 2 of these diffusing together, and so we can now put this back into kinetic Monte Carlo simulations and simulate. You can see how it's ultimately migrating across the surface. It's 1 atom at a time. So this works fine for smaller particles. It diffuses quicker this way. When you start looking at larger particles, you run into issues because you've got all of these atoms skating around the outside, and that begins to slow the process down. And so coalescence versus migrating along the outside become about the same. So you see changes in the diffusivity as you increase the number of atoms, and these are changing almost by a factor of 10 in each of these cases. And you see the differences, at least for the small particles, for rotation versus translational mobility. That's on the alumina terminated surface. We've also done this on oxide surfaces as well, terminated surface, as well as the hydroxylated surface. So I've talked predominantly about silver clusters. we can also have mobile intermediates. So you expose this to water, you might have silver hydroxide, you might have silver chloride. This would strengthen the bond with the silver, but weaken the bond between silver and the surface. And what you find, I won't go through those details, is that silver is the slowest, and the more rapid species to migrate would be things like silver hydroxide and silver chloride. Okay, so a summary on this aspect, which is the diffusion, is that diffusion of clusters occurs very rapidly if the surface is terminated as an aluminum terminated surface. Essentially, if you've got an oxide surface or a hydroxylated surface, that inhibits the diffusion of these small mobile intermediates along the surface. So the next step is looking at, which would be actually the first step, is the detachment, and then ultimately the reattachment is microscopic reversibility in this system. And so we analyze various different clusters. This is a 2-atom cluster on an alpha aluminum oxide. You find the barrier here to dissociate this, to push these guys apart, is on the order of about 0.4 eV. So it's not all that high. You're breaking a single metal-metal bond in terms of doing this. When I go up to larger clusters, and we've done this for 1, 2, 3, all the way up to 25-atom clusters or so, in this case, you find the barrier goes up to about 1.4 eV, because the atom that's ultimately coming off is you're breaking at least 3 metal-metal bonds in the system. So you expect it to be about a factor of 3 higher, because you're breaking many more bonds to carry this out. So the barrier ultimately tends to go up with the metal coordination number of the system. So here are a summary of some of the results, 2, 3, 4, etc., and you find that the barriers ultimately increase in doing so. But if you look closely, you see some deviations in here, and I'll talk about that in a moment. When I move to a hydroxylated surface and then an oxide-terminated surface, what I find is that it's actually easier to detach from the growing particle on that surface. Why? Because this is more acceptive of those metal atoms, the hydroxylated surface and the oxide surface. So I only have the overall energies here, but the barriers scale linearly with these, and so you see that it becomes easier on these surfaces to ultimately more favorable for silver atoms to spill out from the original particle. So if I look at, and now I want to understand a little bit why. So as I look at some of these clusters, I see differences in the barriers, and I also see differences in the charge distribution. So this is looking at a charge analysis on these particular clusters, 1, 2, 3, 4, etc. And what you find is that the charge is much more positive on silver 2, much more positive on silver 4, and then you start to see that it'll change differently. And then it goes down in this case. The larger particle, the larger positive charge ultimately leads to faster movement of the silver atoms on the support. Well, why is it more positively charged for these smaller particles? Ultimately, this scales very directly with the electron affinity of the cluster itself. And so what you find is the electron affinity, it has a much higher, a much lower affinity essentially for 2, as well as 4, 6, 8, etc. And so it does not want to hold on to that electron so easy. It would much rather give that electron up to essentially to the surface. And so we see increases in diffusion in those particular cases. So that's why you see some of the initial oscillations for the very small particles. Once you get beyond a certain size, this tends to simply increase linearly, and this is all due predominantly to the metal-metal interactions. So you've got many more metal-metal interactions than you had in these smaller particles. So we can directly compare sort of the experimental electron affinities with the calculated reaction energies, and we find that the reaction energies scale with the barriers, and so we tend to get a direct correlation between the electronic structure of the particle in the gas phase and ultimately how it may diffuse on the surface. What's even more important, as I pointed out, is the number of metal-metal bonds that you're breaking. So the change in the silver coordination number of the parent cluster that you're looking at, the bigger this number, the larger the activation barrier. You see 2 different slopes, one that deal with even number silver clusters, one that deal with the odd number silver clusters, and they coalesce at some point. But here you find that as I change coordination number, it gets larger, the barrier ultimately goes up. That means I have to break more metal-metal bonds in order to get it to detach from the surface. The overall energies that I showed you here scale directly with the barrier. This is an Evans-Polanyi relationship, and you might expect that in these cases. So now what happens when you start to look at 3-dimensional particle shapes? A lot of the same trends. So we can diffuse this atom, this atom, this atom, and what we're looking at is which layer and what is the coordination number. The metal coordination number here is 3, CM3. It's layer 3, which is described as L3. This one has 3, but it's sitting in the top layer, so it's L1. So we've looked at ultimately breaking these bonds from this particular cluster, coming from different positions. The ones that say CN, coordination number of 6, have the highest energies, most difficult to break because you're breaking, again, more metal-metal bonds in so doing. In the cases where you have coordination number of 3, these are significantly lower, and you expect that from coordination number 6. We see this also for the silver 22 clusters, a somewhat larger cluster, but again it scales with the coordination number. Coordination number of 6 is about 1 eV, coordination number of 7 is about 1 eV, and these are about 0.5 eV. So as you would expect, I showed you previously, the elementary barriers and the reaction energies scale linearly with the coordination number of the metal atom to which the migrating species that comes off the surface has to ultimately detach from the surface. This comes back to one of Stu's points about wetting. All of that was on the aluminum terminated surface. As I start to look at the oxide surface or the hydroxylated surface, you start optimizing some of these metal particles. You see the three-dimensional shape ultimately begins to wet the surface easier. Why? Because you now have stronger metal-oxygen interactions with the support, and those tend to dominate over the metal-metal bonding interactions. If you have weak interactions with the support, you tend to form more three-dimensional particles. And so this would ultimately enhance the idea of coalescence in some of these particles, and I think that nicely combines with some of the things that Stu was saying in his system. So a summary from the detachment: the barriers for detachment are high for diffusion on the support. For the alumina terminated surfaces, the detachment tends to be controlled by the metal atom coordination number, and smaller clusters strongly interact with the support in these surfaces. And this can be explained by the electronic structure of those clusters. So we're taking this information now, and we've developed rules by which we can now deposit particles on surfaces and begin to look at, this is an oxide surface, ultimately diffusion, if we start with the sequence of different metal particles in terms of how they would likely coalesce and form larger particles, and determine the kinetics for these ultimately from the first principle calculations that we've developed. And so that's where we're going in the future with some of this work. I'm going the wrong way. So let me summarize. I've shown you essentially two specific areas: diffusion of mobile species along the oxide surface. This is controlled by the nature of the mobile species, whether it's silver, silver chloride, silver hydroxide, silver oxide, the composition of the support, what is on the surface functionality, if you have other components on the surface, defect sites that may be present in the surface. When you look at the detachment or reattachment energies, these are going to be controlled by metal-metal bonding in that system. The metal-metal bond strength as compared to the metal support bond strength, the size and shape of the particle, and the influence of any adsorbed intermediates may have on these, and again the specific location of the mobile intermediates in these systems. And with that, I'll acknowledge again the support from CRI International, which is an affiliate of Shell Global Solutions, and we'll be happy to answer any questions.
We have time for just one or two questions. Again, if you could just make your way to the microphone and state your name and affiliation and ask your question. Okay. All right. We're just bumping up against the time anyway. So let's thank that again.